So welcome to the Picture Language Seminar. We're very happy today to have Yue Lu. Yue has been at Harvard for 11 years, originally was born in Shanghai, did a postdoctoral fellowship at APFL in Lausanne, and will tell us today about learning by random features and kernel random matrices, sharp asymptotics, and universality laws. Yue, it's really a pleasure to have you, and we're looking forward very much to your talk.
Thank you very much, Arthur, for the invitation and introduction. Today, I'm going to present some of our recent work on understanding a class of nonlinear random matrices that arise in learning and signal processing. In particular, I'm going to show how to obtain some asymptotics of these random matrices by using a fairly general universality phenomena. So when we speak of asymptotics and universality, we are inherently assuming that we are going to work in the high-dimensional setting. And I'm sure everyone has heard about the so-called curse of dimensionality. This is a term coined by Richard Bellman in his book on dynamic programming. Essentially says that a naive exhaustive enumeration in high-dimensional space is not going to be computationally tractable because the complexity grows exponentially. There can also be, in addition to these computational issues, there can also be some counterintuitive phenomena in high dimensions. And here I'm going to just use a very, very simple example to illustrate this point. Suppose we have a very simple task of estimating a vector psi. And then without loss of generality, we can assume psi is pointing towards the North Pole, and x is our estimate. And then we're going to measure the quality of this estimation by the angle theta between the two vectors. And suppose we have a very modest goal. Our goal is just to have an estimate such that angle is less than 89 degrees. Okay, so this looks a very, very simple task. So simple that we feel we can just do a random draw of an estimate from a sphere. We should be able to do a reasonable job. And here, what I show here is just a probability of success if you pick a point randomly, a uniform at random from the sphere. And initially, when the dimension is low, the horizontal axis is dimension, the probability of success is pretty high. But as you grow the dimension, then quickly, the probability of success of getting an estimate whose angle is less than 89 degrees is converging to zero very fast. And what is going on is that our geometric intuition about the sphere is no longer accurate. Instead of thinking about a sphere as something on the left, a more accurate cartoon is something on the right, where if you look, if you can see, there's a central dot. This dot in the middle is the orientation, the North Pole that we want to estimate. And the green region is 89-degree cone on the sphere. They only occupy a tiny fraction on the sphere. The majority of the sphere is occupied by the gray region, which are essentially a narrow band around the equator. So this is a more accurate cartoon. Of course, this is a so-called concentration measure, which says that if you pick a point uniform at random from the sphere, then with high probability, all of these points will be living in a very narrow band of with 1 over square root of n around the equator, right? Okay. So instead of dwelling on these counterintuitive phenomena or computational challenges in high dimensions, the main message that I want to convey in this talk is that there are also many very nice properties happening in high dimensions, and we can call these the so-called blessings of dimensionality. I believe that term was first coined by Dave Donahoe. And here is a list of such blessings. The first one is the concentration measure that we just mentioned. Essentially, it says that many random quantities tend to tightly concentrate around their deterministic limit when you go to high dimensions. And because of this, we can use very powerful methods from statistical physics, from probability theory, to obtain sharp characterizations of these quantities, which would be otherwise very hard to do in moderate or low dimensions. Now, the third blessing is so-called approach into continuum, which says that in high dimensions, with proper rescaling of either space or time, you can convert a discrete description of a problem to a continuous description of problem. One example is the so-called propagation chaos. If you study an interactive particle system with some symmetry and with some proper scaling, you can say that the scaling limit of this system is described by a set of a partial differential equation, for example, the classical McKean-Vlasov type of dynamics. And this is indeed a blessing because you can study more complicated discrete systems by using continuous domain tools, such as partial differential equations. But in this talk, I'm going to focus the last item on the list, so-called universality, and which essentially says that many large random systems tend to be asymptotically equivalent, although they can be very different in their detailed constructions. And again, here, because this is a very diverse background, so I'm going to use a very, very simple example to illustrate the point of universality. The example is the following. Suppose you have an n by n matrix. You can think about n equal to 2000. So 2000 by 2000 matrix, and then we're going to fill each entry by an independent random variable, okay? And with zero mean and univariance. For example, you can just fill these entries by ID Gaussian random variables or ID Bernoulli random variables with proper normalization, okay? Now, because this random matrix is not symmetric, so the eigenvalues, the 2000 eigenvalues are not going to be real valued. So we're going to plot the eigenvalues on a complex plane. And this is what you would get, right? The eigenvalues, the density of the eigenvalues are uniformly distributed over this unit circle, right? This is, of course, the classical circular law. The actual location of each eigenvalue is, of course, random, but the macroscopic property in terms of density is deterministic when the dimension is very high. Right? And this is indeed a phenomenon of universality, because here we're not making further assumption on the distribution of these random variables. The only requirements are that they have zero mean and univariance. And there's actually more to the story. So here, this is a deterministic example, but what if we have these are random examples, but what if we have a deterministic deterministic matrix? So in this case, what we do is to fill the entries of A with the first 4 million digits of pi. So these are totally deterministic. And then we get, again, a 2000 by 2000 deterministic matrix. Of course, we have to do some normalization. We want to subtract the average so that it's zero mean, and we want to normalize it so that the variance is equal to 1. And the eigenvalues still have the same general properties such that the densities are convergent to a uniform distribution over the sphere. This is a quite amazing phenomenon, right? Now, what I'm saying is universality is indeed a blessing in high dimensions. Why? That is because suppose we want to study a system, let's call system A, and from our problem, but for some reason we don't know how to analyze A, potentially because we don't have the right mathematical tool for analyzing A. But if we can show first that A belongs to the same universality class of B and C, some alternative systems, we might as well study system B if it has additional properties, for example, symmetry that we can exploit. And knowing that whatever properties that we derive from B can be carried over to A due to universality. Okay? And next, I'm going to use one example to show how we exploit this so-called blessing of dimensionality. And this is so-called learning by random features. This is joint work with my students, Honghu and Osama Bifala. And here are some of the references. Now, first of all, just as I want to use a slide to show what is the central object that we study in this work. So first, as a reminder, what are the classical linear random matrix ensembles? The first example is the following. Suppose we have a matrix X. You can think about the columns of X as data vectors from your training samples, from your applications. You know, every column is a new data sample. Typically, we assume all these different columns are independent. You have a total of n such vectors. Each vector is of dimension d. And a typical random matrix example that people study is so-called Wishart ensemble. You just look at X times X transpose. From a statistical point of view, you can think about this matrix as empirical covariance matrix. Now, if you plot the eigenvalues of these random matrices, of course, you get the Marchenko-Pastor law. if the dimension is high enough. And the different shapes depend on the ratio between the two parameters, D and N. For different ratio, you have different Marchenko-Pastor, different type of empirical limiting distributions. A second type of classical random matrix is a product of two independent matrices. Here, X is data matrix that I mentioned. F can be an independent matrix. And then you look at their product, and the limiting singular value distribution can also be easily characterized, for example, in terms of free convolution. But in this talk, we're going to consider nonlinear versions of these two ensembles. In particular, the nonlinearity is represented by a sigma, and this is an element-wise nonlinearity. So that means we are going to apply a nonlinear transformation to each entry of X transpose, or to each entry of F times X, okay? And nonlinearity can be fairly general type of nonlinearity. So why do we want to study these? There are a few applications where such nonlinear transformed version of random matrices appear. The first one is about shrinkage of covariance matrices. Maybe the covariance matrices that you obtain are noisy for various reasons. You want to shrink, apply shrinkage to different entries of these covariance matrix. And a second type of application where these kind of matrices arise is the setting of a kernel learning. So if you want to study machine learning by using the kernel method, then you will encounter the first type of nonlinear random matrix. Okay, apply a nonlinearity to a symmetric random matrix. And the third type of application where these kind of nonlinear random matrices arise is a so-called random feature model. And this is what we are going to talk about in the rest of this presentation. Now, first, as a very quick reminder of what the supervised learning setting that we consider, the setting is the following. Suppose we are given a collection of training samples, xi and yi. So you can think about xi as a vector representing an image of either a cat or dog. Okay, suppose you have a 25 by 25 image, then you are essentially treating each image as a 625 dimensional vector, and yi is a label, right? Equal to 0, cat, 1, dog. Now, in a simple setting is when these data points, from the two different classes, are linearly separable. So that means if you visualize all these points in the 625 dimensional space, they can be separated by a hyperplane, right? This is a simple case. So if this is the case, then we just need to learn a separating hyperplane. And this hyperplane can be parameterized by its normal direction. So in this case, we might as well study a vector W, right? This is the normal direction of this hyperplane. And in practice, how this is done is we solve an optimization problem where we want to search for the optimal separating hyperplane parameterized by this vector W. And then in this optimization problem, we have two parts. The first part is so-called loss function that measures how well this particular hyperplane indexed by W is predicting our labels. And then we can also add potentially a regularizer. So here I just give a few examples of the loss function that is typically used in machine learning. For example, you can use square loss, exponential function, logistic loss, and so on and so forth. And you can also use a rich regularization, meaning you just try to minimize the L2 norm of the weight vector, L1, or a combination of the two. These are typical choices people use in practice. Okay, but what we want to do is to have theoretical analysis of the performance of this learning problem. But first, let's consider a more challenging setting, because in many cases, the data, in this case, we visualize these as red dots versus blue dots. They are not linearly separable. They cannot be separated by a hyperplane, but they can be separated by some nonlinear curve. So then typically the strategy that we apply is to do a nonlinear mapping, so-called feature map. You want to map the original data from d-dimensional space to a p-dimensional space. And the mapping is nonlinear, with the hope that after this nonlinear mapping, in the mapped p-dimensional space, these red versus blue dots can be linearly separable. Okay? So this is the idea. Now, right now, a very popular strategy for performing this nonlinear mapping is just to do a multi-layer neural network. So in this case, the input is the d-dimensional vector, okay, an image, and then you multiply it with some weights, and then you apply element-wise nonlinearity, and you can iterate this process. You don't need to stop at one layer. You can have multiple layers, but at the end of this transformation, you get a p-dimensional vector. And the p-dimensional vector, if you have chosen these mapping correctly, then this p-dimensional vector are linearly separable. And then you are just going to learn this weights W1 to WP as the weights for the parameterizing the separating hyperplane. Okay? So this is the idea. So in terms of the training process, essentially what we're doing is something very similar to what we have seen before. You are minimizing the summation of a loss function and the regularizer. But in this case, what you need to change are both the weights at the last layer about the hyperplane and also the parameters of the feature learning, feature mapping. So in this case, the parameter is just F, the weights for the weight coefficients for the first layer mapping. Okay? So the minimization problem is over W and F. So this is one way to think about a neural network, how learning is done. Now, we're going to consider a simplified version of this problem, the so-called random feature model. So what random feature model does is the following. We don't learn this F. Again, just to remind everyone what F is. F is the coefficients in the first layer. It's a matrix, okay? So we're not going to learn F. We're just going to initialize F with some random weights, and we keep these weights frozen. So these are the weights. And the idea is that if we can map the original d-dimensional space to a much higher dimensional space, in this case, P is much larger than D, then we sort of have done a lot. We have a lot of diversity built in the feature map. And then we're just going to use this as our feature map. There's no further learning. And this is, this idea was proposed independently in different places. For example, in the work by Rahimi and Rat, the original motivation to have a Monte Carlo efficient implementation of a kernel method. But the same idea also appeared in earlier work under the name of stream learning machines. Okay, so this is the setting. We're going to consider a learning problem where the feature map F is random but frozen. Okay, and then we're only going to learn the weights at the last layer, W, and we're going to solve this optimization problem. Now, what we want to do from our point of view is to understand the theoretical performance of this optimization problems. So in particular, we care about two quantities. The first quantity is so-called the training error, meaning that suppose you are given a collection of training samples. In this case, these are the training samples, I from 1 to n training samples, and n labels yi. We want to know what is the value, the minimum value of this optimization problem. And the second quantity that we care about is so-called test error. Suppose we have learned the optimal weights. In this case, we write the optimal weights as W star. That's a solution of this optimization problem. Then we're given a new training sample and a new label. How would this new trained weights predict the new label? Okay, so this is the performance of our learned architecture for predicting a new label. Now, to do theoretical analysis, we have to make some further statistical assumptions on how the data are generated. So typically, the assumptions that we make are the following. First of all, we consider the so-called teacher-student model, where we assume that our label yi is generated by some unknown function, teacher function. It's a function of the input vector xi. Okay? And the second typical statistical assumption that we tend to make is that the input data x1 to xn are independent, and each entry can also be independent. Furthermore, you can even assume they are independent Gaussian vectors. So this is the typical simplifying assumption that we want to make. Because we want to know the exact value of training and testing errors, then we have to make these additional statistical assumptions on how the data are generated. Now what is the results in the literature? So there have been a lot of results in the literature, analyzing problems like this, but typically under some additional assumptions. The additional assumption is for a special case when the nonlinearity sigma, this is the nonlinearity that you apply, is just x. So it's a linear function. So in this case, if sigma is equal to x, then each training sample x of I is a Gaussian random vector for any given f, then our feature vectors are just ID Gaussian vectors with a given covariance matrix sigma determined by f, right? So this is a special case, but for this special case, there are a lot of available mathematical tools for analyzing the performance of the optimization problem that I mentioned. So here I just list some of the very popular tools people have been using successfully to analyze the optimization problem. So depending on the background of the audience, early methods include the replica method from statistical physics. And then more recent methods include the Gaussian width, statistical dimensions, Gordon's comparison inequalities, message parsing algorithms, and leave one out analysis, or so-called cavity method from statistical physics. So I don't want to go to the details of these actual methods, but the main message is that it's a very nice playground for theorists if the feature vectors are Gaussian or something like a Gaussian vector. So because we have a lot of available theoretical tools. But the challenge here is that in the random feature model, we have a real nonlinearity sigma. So in this case, the feature vector is a linear mapping of a Gaussian vector. So these are no longer Gaussian. And so the tools that I mentioned for Gaussian models are no longer applicable. So this is the challenge. But fortunately, what people recently observed in the literature is that there's a way to get around this challenge. And then for that, we need to consider two different versions of the feature map. The first version, the nonlinear feature map, is the one that we want to study. So here, again, X is your random matrix representing your input data. And F is just a random weight matrix from the first layer. It's random, but kept frozen. And then sigma is the nonlinear transformation applied to each entry of this product. Now, we can consider an alternative version, which we call the B version. The B version is of the following form. B can be written as a constant mu0 times an all one matrix, plus another constant mu1 times f times x. Okay, so it's linear. There's no nonlinearity. And you also need to correct this B by adding a third component, which is another constant mu2 times z, where z is an ID Gaussian matrix independent to everything else. Okay, so this is a different random matrix ensemble. A and B are totally different. And for each, and here, these are the formulas for how we compute these coefficients mu0, mu1, and mu2. So here, just we take expectation of sigma, the nonlinearity, applied to G, where G is just a standard Gaussian. Okay. Now, I'll come back to this point. Is actually the coefficients have a meaning, exactly why these coefficients are chosen this way. Now, for the A and B versions, you can calculate, or you can define the training error for the A version and training error for the B version, and a testing error for the A version and testing error for the B version. As a reminder, what we care about are these two quantities, the training error of A and testing error for A. Okay, we want to know their limits in a high-dimensional regime. Now, I also want to add that you can think about B as another type of feature map. It is a linear feature map, so you just have F times X, but it's also noisy because we need to add additional independent Gaussian noise to the feature map. It's a noisy linear feature map. Okay? Now, what people have observed in the literature recently was the following conjecture or phenomenon, so-called Gaussian equivalence phenomenon. So roughly speaking, what people have observed is the following: for all generic matrix F and for all reasonable nonlinearity sigma, then the training error and the testing error of the two versions are asymptotically equivalent. Okay, so this is this phenomenon has been observed in a sequence of recent papers, and they have also been exploited as something that you can use. Okay. Now, first, let me say why this phenomena is something that is potentially very useful if we can rigorously prove the equivalence. So, why is it useful? Here, what I show are some simulation results. If you look at the figure on the left, the orange dots are, in this case, the training and the testing errors for the original nonlinear feature model. Okay? And black crosses are the corresponding quantities for the linear noisy version. You can see they fall right on top of each other. I guess I remember the dimension that we use in this experiment is about n equal to 2000, d equal to 1000, something at this scale. So you can see in this dimension, the two quantities already match very well. But what is very nice is that for the linear Gaussian model, we have the available theoretical tool for predicting the analytical limit of these quantities. And here, the green line and the blue line are the theoretical curve that we can derive based on the Gaussian model. Okay, so we can see that these theoretical curves can very accurately predict the actual performance of the random feature model. Okay. Now, this is indeed what we did in our recent work with my student Osama Difala, and then we use so-called Gaussian comparison inequalities for studying this model. So what we show is that I think I have to be more precise. In this case, it should not be the A version, it should be the B version, because we haven't established the universality yet. We're just saying that if there is this universality, then you get to study the linear Gaussian version, then the training error and the testing error of the linear Gaussian version will converge as the dimension of this D and N go to infinity at a proportional rate, then the training error and testing error will converge to deterministic limits. So I don't want to go to the details, doesn't matter. So essentially, these are some deterministic functions that we can calculate. Okay? These are low dimensional functions, but yes, changes.
Yeah, thank you. You just a clarifying question. The noise that you add, is this a static noise, meaning you add it once, or is this sample for every sample? Example.
Sample for it's yeah. So let me go to the slide so that I can answer your question precisely, and also I want to repeat the question. So let me go to the place where we define the B version, right? So in this case, because the notation here we're using the matrix notation, then the A here is F, which is a matrix, times X, and then you apply sigma, right? So you have different columns. You have n columns for n data points. Similarly, B here, you have the same dimension. So Z is a Gaussian matrix. So we are applying an independent noise to each independent sample. Yes. So the noise is not frozen. So the noise is new for every new sample.
Oh, that's really interesting. Okay. And just while you're on the slide, so when you click, you have this G appearing in the
Yes.
what,
Yes.
what is that G?
So G here is just a standard Gaussian.
Oh, okay, that's what it is.
So and then mu0, mu1, mu2 are calculated in this way. So you know sigma, for example, sigma is tanh, then you can calculate the exact values mu0 to mu2.
I see. Okay. Oh, thank you.
Sure. All right. Okay, so let's go to let's go to this this slide where we exploit the equivalence. So far, again, let me emphasize, so far we're not saying we're proving the equivalence, but we're just, for now, exploiting this equivalence. If A and B are equivalent, B is belongs to the Gaussian ensemble, we can have a lot of tools. And in this case, just analyzing this Gaussian model is an interesting problem in itself, because it's still not a very easy task. And here, what we want to do is to study the training, in this case, the training error and the testing error. Both of these quantities come from a optimization problem, high-dimensional random optimization problem. They are not deterministic closed functions with closed form expressions. They are implicitly defined functions. So the kind of tool that we use is so-called a Gaussian comparison inequality, because we are studying Gaussian ensembles. What we do is we can define two Gaussian processes, which we call X and Y. And here C is just a Gaussian matrix, and G and H are two Gaussian vectors. Okay, so these are the two Gaussian processes indexed by vectors U and W. But why do we want to study these two Gaussian processes? That's because on a high level, the optimization problem associated with our training processes can be converted into a minimax value of the two Gaussian processes. In particular, this quantity, the minimax value of these Gaussian processes has a one-to-one correspondence to our training error. Okay, so I skipped a lot of details, but the picture here, the main thing here is that to study the training error, essentially it boils down to studying or knowing what is the minimax value of this Gaussian process. Now, correspondingly, we can define the minimax value of the Gaussian process Y, where Y we call it the easy version, because if you look at the definition of the Y, there's no matrix involved. There are only two Gaussian vectors. Okay? Now, the main tool that we use is a comparison inequality from Gaudin's result. What Gaudin showed was the following. For any dimension, then you can have this inequality. So for any constant C, the probability that the quantity that we care about, phi hard, less than C, is bounded by 2 times the probability that the easy quantity less than C. Okay, so this is a very useful property, because typically this quantity concentrates around a constant as dimension go to infinity. Suppose this is phi easy concentrate around this constant. And then we say if we pick C to be this constant minus epsilon. So you have a C star, and then you have C star minus epsilon. Okay. Then we know that the probability that the phi easy less than C star minus epsilon is going to 0. And because of this inequality, then probability that phi hard also less than C star minus epsilon also goes to infinity. In other words, if we can show that the easy version concentrates around a constant, then necessarily the quantity, the hard version, the quantity that we care about, is going to be lower bound, essentially lower bounded by this quantity. So we have a one-sided inequality from Gaudin's comparison theorem. But the nice thing is, if we were working with a convex problem, then you get to flip the direction of this inequality, then you get the two-sided bound. Okay, this is just a very high-level view of the kind of technical tool that we use to analyze the Gaussian problem. Okay, so if you are interested in the detail, I'd be very happy to talk to you offline about this. But what I want to really spend more time on is how to prove the equivalence conjecture, meaning just to show that indeed the A version, the nonlinear version, is equivalent to the B version, the linear version. Okay, so I'm going to provide some intuitive explanation for why the equivalence can be true. There are multiple levels how we can understand this equivalence. The simplest explanation is the following. If you look at the A version, but again, because here F is a matrix and X is just a, this is X is a matrix with different columns. So if we look at each column of A, let's call A is a matrix with columns A1, A2, A3, and up to A of n. Similarly, for the B version, we have a matrix B is equal to a matrix with these different columns. Okay, all of these are random vectors. If you look at their empirical, their expectation and covariance of A and B, with the choice of the coefficients that we have chosen here, then they are essentially matching. So what we're saying is, at this level, it's a very, very simple explanation. They are equivalent because of universality, because they have this matching first two moments. The expectations of the random vectors are essentially matching. The covariance of the random matrices are also essentially matching. Then we can say the two versions are going to have the same asymptotic training and testing error because of universality. Of course, this is just a very simple explanation. And here we also have some additional assumption on the F matrix. Essentially, we want F to be having nearly orthogonal rows. But there's much more to the story. So what I want to say is a different view or a different explanation for why we have this universality. And I believe this is a much more fundamental reason why we have this universality. Now, first of all, just as a reminder about Hermite polynomials. So Hermite polynomials is a sequence of orthogonal polynomials, starting from 1, the constant, and then the second Hermite polynomial is x, and then you have a quadratic, and so on. They are indeed orthogonal and with respect to weight function given by the PDF of a standard Gaussian random variable, right? And then the picture on the right shows the first 5 Hermite polynomials that we have here. Now, because the Hermite polynomials form a complete orthonormal basis, then we can expand any square integrable nonlinear function sigma of x as a linear combination of all these Hermite polynomials. Mu0 h0, mu1 h1, mu2 h2. The mu's are the expansion coefficients, and hi's are the Hermite polynomial at ith order, right? Now, because we are applying this nonlinearity to each entry of the random matrix, so we can write the random matrix A, which is sigma of f times x, as a linear combination of individual random matrices, where each random matrix, for example, H1, is just applying the first Hermite polynomial entry-wise to the random matrix f times x, so on and so forth, right? So we can write A as a linear combination of these random matrices. Now, what is a more refined equivalence phenomenon? The more refined equivalence phenomenon is the following. So because our matrix A can be written in this way, A is a linear combination of these HIs, then in a high dimensional limit, what happens is that we say A is equivalent to B, where B can be written again as a linear combination of random matrices. But what we do is we keep H0. And remember, H0 is just constant. So in this case, H0 is just mu0 times an all-1 matrix. And plus mu1 times H1. H1, the second Hermite polynomial is a linear function, x. This is just f times x. But what we do is we're going to replace, starting from the third Hermite polynomial, replace each such random matrix by an independent RID Gaussian random matrix. Okay, so this is really what's going on about the equivalence. Okay, And what are the mu's? Previously, I showed the formula for the mu0, mu1, and so on. Is actually the formula comes from this Hermite expansion, right? So the way we calculate the mu's is actually to calculate the expansion coefficient with respect to different Hermite polynomials. Okay. So, and I want to emphasize that a similar idea appeared in earlier version in the random matrix literature, especially the work by Chen and Amit Singer. So they study a symmetric version of this matrix, and they characterize the asymptotic spectral density. But in this equivalence is inherent in their analysis, but they didn't explicitly state that actually what is happening is asymptotically A is equivalent to B, where we get to replace all the higher order Hermites, starting from the second H2 by an independent Gaussian. Okay. All right. All right. So, but why is this true? So this has to do with some harmonic analysis. So if we look at the Hermite polynomial, so in this case, ij's entry of hk is just equal to applying a kth order Hermite polynomial on the inner product between two vectors. The first vector is coming from the F matrix. The second vector comes from the data matrix, F and X, right? Okay. Now, in the high dimensional limit, Hermite polynomial is well approximated by something so-called ultraspherical harmonics polynomials, or so-called Gegenbauer polynomials. Now, for Gegenbauer polynomials, we can have this very nice expansion formula. So essentially what we're saying is this nonlinear version of inner product can be linearized as a linear inner product, but each element of this linear inner product is spherical harmonics. Okay, so YKJ is just a particular spherical harmonic at a kth order and a jth such spherical harmonic. Okay, so this is the first formula that we're going to use. The second property that we're going to use is that because the original data are symmetric, they are sort of uniform distributed on a sphere, and then there is a important property of spherical harmonics is that if you look at the expectation of the product of two spherical harmonics, and expectation is equal to this formula. Essentially, what we're saying is all the spherical harmonics are uncorrelated, and they have univariance and uncorrelated, right? Then, because of this, if you look at each entry of our nonlinear matrix, each entry can be written in this form. And if we replace all these spherical harmonics by independent copies, then by using a central limit theorem argument, then each entry of this nonlinear matrix is indeed going to be a Gaussian random variable in a high dimension limit. Okay, this is just by central limit theorem. But in addition, when you look at starting from H2 and H3, H4, and so on, NK, the number of terms to be summed is much larger than the underlying dimension N and D. In this case, because of this fact, you can show that the correlation between different entries of the nonlinear random matrix are weakly correlated. So in the high dimension limit, they can be approximated by an independent ID Gaussian matrix. So this is just a high-level explanation of what's going on with this equivalence. Okay, all right. So here is just some slide to show that we proving this equivalence under some additional technical assumptions. We assume that the loss function that we use in the training process is a convex loss function. And then the regularizer is strongly convex. These are technical assumptions. We also assume that the weight matrices are independent Gaussians. And there's also some limitation. We are assuming that the activation function sigma of x is an odd function. This is a technical limitation of a proof, although the equivalence principle works for generic sigma. Okay. Under these assumptions, that what we proved is the following type of characterization. We show that if you compare the training error of the A version and B version, then necessarily you have this inequality. That means if the B version concentrates around a constant C, then necessarily the A version also concentrates around the same constant C. So they have the same asymptotic limit. And this is also, these two inequalities are symmetric. Okay, so that means that they must have the same asymptotic limit, right? There's some finite sample type of rate in terms of how well this equivalence works for finite dimensional P. I don't have time to go through the actual proof. That I just want to highlight some key idea or key challenges in the proof. So let me just highlight one key challenge in the proof. The key challenge is the following. So we want to show that this quantity, the training error of A version, is equivalent to the training error of the B version. But the challenge, and then here A version comes from the nonlinear random matrix, and B version comes from these linear Gaussian random matrix. The main challenge comes from the fact that these quantities are not explicitly defined functions. They are implicitly defined through some high-dimensional optimization problems. So, it's more challenging to prove the equivalence for this type of quantities than, for example, to prove that the A matrix and the B matrix have the same asymptotic limiting spectrum, right? This is one of the main technical challenges. Now, in our actual proof, what we use is the classical idea of Lindbergh's replacement trick. So what we do is we consider the A version which has n different columns, random vectors, and the B version has n different columns. What we do is we are just going to replace one column of A by one corresponding column of B, one step at a time, right? So first step, you replace A1 by B1, second step, A2 by B2, and so on and so forth. Now, the key thing to know is that we only need to do n steps to convert from A to B. And to show equivalence, we just need to show that the amount of error or difference incurred in each change or swap is of order little O of 1 over n, because you are going to do it n steps. Then by using a telescoping sum, as long as the amount of difference incurred in each swap is of this quantity, then the total number of errors that we incur after doing n steps is a little over 1. Okay, so this is the idea. And then in actual proof, we also need to use some Stein's method to show a version of central limit theorem. And as I mentioned, one of the challenges to deal with this implicitly defined function through an optimization problem. For that, we use a so-called leave one out analysis for analyzing this optimization problem. Okay. But I don't want to go to the details. I'd be very happy to talk to you offline if you're interested. All right, just as a summary. So in this talk, we studied a sort of a class of nonlinear random matrices that arise in machine learning. In particular, we consider the so-called random feature model. And we established an asymptotic equivalence between this nonlinear ensemble and a linear Gaussian ensemble, which is much easier to analyze. So this is why we call it a blessing of dimensionality. And because we have established this equivalence, we get to study the easier to work with Gaussian version, and then we can obtain a sharp asymptotic characterization, the performance of the random feature model by studying the equivalent Gaussian version. Okay. All right. Thanks for your attention. I'd be happy to answer if there's any question.
Well, thank you very much, Yue, for an absolutely beautiful introduction to this subject. There's so many things that seem to connect with what other people are doing, and it's exciting. So I hope there'll be a great deal of discussion now. Please turn on your video so we can see who talks. And maybe I should start with a general question. You gave this beautiful understanding of approximating the nonlinear system by one connected with a Gaussian. Is there any other system aside from the Gaussian, or is there some fundamental reason that the Gaussian is the one with Hermite functions to compare
so
to?
the Gaussian doesn't matter. So in this case, we can also say the equivalent version has. Let me go to the this equivalence. So in this case, we can also have f and x to have ID entries, and Z also have independent. Z is independent to f and x, but ID entries without Gaussian distribution. But it is particularly convenient if you if you establish equivalence to the Gaussian case, because as I mentioned, there are a lot of tools that are tailor-made for studying Gaussian ensembles. Okay.
Gaussians are wonderful for computation, and I'm very familiar with Gaussians, as many people here are from quantum field theory.
That's right. So it's just convenient to once you have a Gaussian, but the actual result is much more robust than that. And so changes.
Yeah, thank you. Really, really nice talk, Yue. I'm wondering if, do you have a version of this for kernel methods? I mean, there the features have orthogonal properties.
Yes, essentially it's a very similar idea. The kernel method is just symmetric version, but the idea, the main idea is just coming from, or if you want to say, if you don't prove it first, you just want to say what is the equivalence, and then you just look at what we have here, right? So you have the key formula is just this formula. You apply a nonlinear function. In particular, any nonlinear function can be written as a linear combination of Hermite polynomials. So just let's look at one Hermite polynomial applied to the inner product. And the two vectors in the inner product are normalized. So they live on a sphere, or asymptotically living on a sphere. Then you have this expansion formula, which go to the spherical harmonics. So this is a lifting because the number of spherical harmonics can be much higher than D. But the nice thing is, if your vectors are sort of uniform, rotational invariant on the sphere, then the spherical harmonics are uncorrelated. Okay. So then if you say, let's just forget about their correlation, let's assume all the spherical harmonics are independent, that's clear why you should get a Gaussian for each Gaussian law for each entry. And it's also possible to understand why a different order of spherical harmonics, different orders of Hermite polynomials, the correlation between different matrix entries can also be very weak, depending on NK, the number of spherical harmonics that you use in the summation. And so the symmetric version is the same, as you can see, right?
Yeah. Yes. Just maybe following up on that. I mean, I wasn't sure you were. Maybe you might be able to get rid of the requirement that X has to be uniformly sampled over the sphere, because in the kernel methods you could work on a basis of features where the features themselves are orthogonal with respect to. Yeah.
Yes.
Okay.
But the challenge, suppose your data is not uniformly distributed on a sphere, not even asymptotically uniformly distributed on a sphere. I believe it's still possible. In this case, you can just say you are applying a different nonlinear function to each entry because you renormalize the inner product. So in this case, you still have this equivalence, but on a high level, you can see this as multiplying element-wise with this Gaussian matrix with a pattern matrix, right? So,
okay. Thank you.
Zichen, you have a question.
Yeah, hello. Thanks for the wonderful talk. I just have a clarification question. So this result. So I was confused when you showed that initially you have the B matrix as just the first two terms of the Hermite polynomial, right?
Yes.
And then that turns out to work already with the central limit theorem. And then but then I thought that you have to have all the terms. This is just the perturbative expansion. Is the central limit theorem, like, is the universality, does the convergence hold just for the two terms, or?
No, it's yes. So I sort of understand your question. So really, what we're saying is the B version that we've written down here should be written as mu0 times 1 plus mu1 times f of x, which are the first and second polynomials, right? Plus mu2 times z2, plus mu3 times z3, plus so on and so forth, right? And the z2, z3 are just independent Gaussian, but because they are independent Gaussian, we get to combine these as a single Gaussian, which we write C here. And you can see the mu2 is just equal to mu2 in this case is just equal to summation of mu I squared I greater than equal to 2 square root. And this is exactly what we have here. So
oh, I see. Okay. Okay.
Because all the remaining high order terms are Gaussian, you get to combine these as a single Gaussian. You don't need to be refined. You can just say everything's Gaussian. The remaining terms are Gaussian.
So Liwan had a question, but maybe I think he had to go to a class, so he's left. Oh no, there you are. Do you have a question, Liwan? You're muted.
Yeah, sorry. My microphone have some problem. So I just have the same question as Zerchen. So thank Professor Lu for solving the problem.
So there are other comments. Tom, it looks like you want to say something.
Well, I was going to ask whether this is a one-layer system that you're describing. So I suppose there are automatic generalizations to multi-layer. Is that correct?
That's correct. That's a very good question. That's correct. It's possible to just extend this argument by doing conditioning, because here when you analyze this matrix, then you can say I don't need to use I don't need both f and x being random. I can just say f is deterministic and x has independent columns, and f will be such that different rows of f are nearly orthogonal, but they're deterministic, conditional enough, right? And then what you do is, suppose you have multiple layers, and then you have sigma of let's say f1 and sigma of f2 of x. Now, the one way to potentially handle this type of problem is just to say that you first study this matrix, and then once you have studied that, you treat this matrix as let's say x of 2. And then in this case, you condition on x2. Then you just use the fact that different rows of f are independent. Then you are getting back to very similar situation. The only thing that we need to prove are with high probability the columns of x2 are close to being orthogonal. So a very similar idea. And I want to mention this idea was used I think by appeared in a recent paper, not from our group, in studying the asymptotic singular value distributions of such matrices.
So Tom, are you thinking of connecting to the renormalization group problem?
No, not really. No, I wasn't. But there probably is some. There may be some connection. I wasn't trying to speculate on that.
So there are other comments.
Yeah, changes.
Yeah, I mean, it's perhaps speculative comment, but I mean, is there another maybe use for this in the sense that, like, instead of doing a nonlinear map, would it just mean that just do a linear map, but add noise to your data, and this is a good way to embed your data to another space?
So in this case, yes. So under the model that we study, under the scaling that we study, yes, nonlinearity is equivalent to noisy linear, which is not a very very nice message, right? Then more important question is what are the regimes or what are the scaling settings such that nonlinearity, genuine nonlinearity, it cannot be reproduced by a noisy linear version.
Let's see.
So are there certain classes of matrices for which you can apply the sigma, not just point-wise, but to the matrix itself?
To the matrix itself, then in this case, then we can approximate. If you are not applying element-wise nonlinearity, you apply to the matrix, then we can potentially approximate it by a polynomial of matrix. Then that setting is can be easier to analyze if these matrices have some nice properties. Suppose all the original matrices have the symmetric, they have a rotational invariant eigenbasis, and then you apply a polynomial of such matrix, then it's much easier to analyze these. The challenge actually comes from the fact that we are applying nonlinearity to each entry of this matrix.
Are there other comments or questions? If not, I'd like to thank Yue Lu again for absolutely wonderful introduction to this topic, and I look forward to hearing much more about it in the future. Thank you. Thank you.
Thanks again for the invitation.
Thank you very much.
Thank you.
Bye-bye. Bye-bye.
Bye-bye.
See you next week. Alan Khan is talking then. Well, that was really nice.